You know, there's something deeply unsettling about looking at the fossil record and seeing the pattern that emerges. 5 times in Earth's history, 5 distinct moments spread across hundreds of millions of years, the planet has experienced what we call mass extinctions. Events where the majority of species on Earth went extinct within a geologically brief period. The Ordovician extinction, about 445 million years ago. The Devonian, about 375 million years ago. The Permian-Triassic extinction, about 252 million years ago, the worst of them all, where perhaps 96% of marine species and 70% of terrestrial vertebrate species disappeared. The Triassic-Jurassic extinction, about 201 million years ago, and the Cretaceous-Paleogene extinction, 66 million years ago, the one that killed the dinosaurs. 5 extinction events in roughly 500 million years of complex life on Earth. That's one every 100 million years or so on average, though the timing is irregular and the causes varied. Asteroid impacts, massive volcanic eruptions, rapid climate change, ocean acidification, oxygen depletion, different mechanisms, but the same result: most species gone, ecosystems collapsed, the planet fundamentally transformed. And here's what keeps me awake some nights. We're in the middle of the 6th one right now. We're living through a mass extinction event in real time, and unlike the previous 5, this one is happening at a pace that's almost incomprehensibly fast, and we're causing it. Human activity, habitat destruction, climate change, pollution, overhunting, introduction of invasive species is driving species extinct at rates that are somewhere between 100 and 1,000 times faster than the natural background extinction rate. Some estimates suggest we're losing dozens of species every single day. Most of them are insects, plants, fungi, small organisms we've never even cataloged or studied. They're disappearing before we even know they existed. But here's the thing that I want you to really grapple with, because it's the uncomfortable core of what we need to discuss. Even if we wanted to stop this extinction event, even if humanity suddenly achieved perfect environmental stewardship tomorrow, if we halted all habitat destruction, eliminated all pollution, solved climate change instantly, it's likely too late. The momentum of extinction is already built into the system. The processes we've set in motion will continue playing out for centuries or millennia, regardless of what we do now. The 6th mass extinction is, in a very real and troubling sense, unstoppable. Now, I need to be very careful about what I'm saying here, because I can already feel the objections forming. Are you saying we should give up? Are you saying environmental conservation doesn't matter? Are you being defeatist? And the answer to all of those is no. What I am saying is that we need to be honest, brutally, uncomfortably honest about the scale of what's happening, about the mechanisms driving it, about what can and cannot be reversed, and about the difference between slowing a catastrophe and preventing it. Because here's what I've learned from studying the physics of complex systems, from understanding how cascading failures work, from looking at the mathematical models of ecosystem collapse. Once certain thresholds are crossed, once certain feedback loops are initiated, the system becomes committed to outcomes that can't be avoided even if you remove the original cause. It's like a boulder rolling down a hill. At some point, it doesn't matter that you stop pushing it. Gravity and momentum take over, and it's going to reach the bottom regardless of what you do. Let me take you through this carefully, because understanding why this extinction is unstoppable requires understanding several interconnected factors: the time delays in ecological systems, the nature of extinction debt, the feedback loops that amplify initial disturbances, the fundamental requirements of species survival, and the sheer scale of human impact on the planet. Each of these alone is daunting. Together, they create a situation where even our best efforts will only determine how bad the extinction becomes, not whether it happens. Let's start with something that sounds almost paradoxical: extinction debt. This is a concept from ecology that refers to species that are already committed to extinction, even though they're still alive right now. They're what ecologists sometimes call the walking dead, populations that are too small, too fragmented, too genetically impoverished, or in habitats too degraded to survive long term, even if no further harm comes to them. Here's how it works. Imagine a species that needs, let's say, a minimum viable population of 500 individuals distributed across a sufficiently large habitat to maintain genetic diversity, find mates, and survive stochastic events like disease outbreaks or bad weather years. Now imagine that habitat destruction and hunting have reduced that species to 300 individuals scattered across isolated habitat fragments. Even if you immediately stop all hunting and habitat destruction, that species is likely doomed. The population is below the minimum viable threshold. Genetic diversity is too low, inbreeding depression will reduce fertility and health. The isolated populations can't interbreed, so each fragment becomes its own genetic dead end. When a disease sweeps through or there's a string of bad years, there aren't enough individuals to absorb the losses and recover. That species will decline and probably go extinct over the next few decades or centuries. Not because of anything new you're doing to it, but because of damage already done. It's committed to extinction. It's part of the extinction debt that's already been incurred but not yet paid. And here's what's truly troubling. We have no idea how many species are in this category right now. Conservative estimates suggest thousands of vertebrate species alone, mammals, birds, reptiles, amphibians, fish, are below minimum viable population thresholds. When you include insects, plants, fungi, and all the other organisms we barely monitor, the number could be tens of thousands or more. These species are still counted as alive in biodiversity surveys, but they're effectively already gone. We just haven't waited long enough to see them disappear. This extinction debt was incurred primarily in the last century or two, as human population grew from 1 billion to 8 billion, as we converted vast areas of forest, grassland, and wetland to agriculture and cities, as we hunted and fished with industrial efficiency, as we introduced invasive species to every corner of the planet. The damage is done, the debt is owed, and it will be paid in extinctions over the coming centuries, regardless of what we do now. Now let me introduce you to another mechanism that makes this extinction unstoppable: time lags in ecological systems. Ecosystems don't respond instantly to changes. There are delays, sometimes decades or centuries long, between a disturbance and its full effects. This creates a situation where we're still experiencing the consequences of environmental changes made decades ago, and the full impact of what we're doing now won't be felt for decades to come. Take climate change as an example. The CO2 we've already emitted will continue warming the planet for centuries, even if we stopped all emissions tomorrow. That's because the climate system has enormous thermal inertia. The oceans alone contain vastly more heat capacity than the atmosphere, and they take a long time to warm up or cool down. We've committed the planet to a certain amount of additional warming just from emissions already in the atmosphere before we even account for the additional warming that will come from feedback loops we've triggered. And that committed warming will continue reshaping ecosystems, shifting climate zones, altering rainfall patterns, acidifying oceans, melting ice, raising sea levels. Species adapted to current conditions will find those conditions changing beneath them. Many won't be able to adapt fast enough. Many won't be able to migrate to suitable habitats because we've fragmented the landscape so thoroughly that there are no connected corridors for migration. They'll find themselves in increasingly unsuitable environments with nowhere to go, and they'll decline toward extinction. This is already happening. We're seeing range shifts, phenological mismatches, where species that depend on each other for food or pollination are falling out of sync because they're responding differently to temperature changes and local extinctions at the edges of species ranges. And this is from warming that's already occurred about 1.2 degrees Celsius above pre-industrial levels. we're committed to additional warming beyond that from emissions already in the atmosphere. And realistically, we're going to continue emitting for years or decades more before we fully transition away from fossil fuels, which commits us to even more warming beyond that. The species impacts of all this committed warming haven't fully materialized yet. We're still in the early stages. The full cascade of extinctions from the climate change we've already caused will play out over the next several centuries, long after we're gone, regardless of what we do about emissions from this point forward. And climate change is just one driver. Let me tell you about habitat loss, which is arguably even more important for most species. We've already converted roughly half of Earth's habitable land surface for human use, agriculture, cities, infrastructure. We've drained wetlands, cleared forests, plowed grasslands, dammed rivers. For many ecosystems, what remains is a small fraction of what existed just a few centuries ago. In some regions, think of the Atlantic forests of Brazil, or the prairies of North America, or the forests of Europe. Less than 10% of the original habitat remains, existing as scattered fragments in a sea of human-dominated landscape. When you fragment habitat like this, you don't just lose the area that's directly converted. You also lose the functionality of what remains, because small fragments can't support the same species diversity as large, continuous habitats. Edge effects penetrate into the fragments. More light, wind, temperature, fluctuation, predators, and invasive species that thrive in disturbed areas. The interior habitat conditions that many species need are lost, populations become isolated, genetic diversity declines, and species gradually wink out, even in the protected fragments. This process plays out over decades or centuries. A forest fragment might retain most of its tree species for 50 years after being isolated, but the animal species that depend on large territories, the big predators, the wide-ranging herbivores disappear within years. Then the species that depend on those species begin to decline. Then the processes those species enabled, seed dispersal, pollination, nutrient cycling, become disrupted. The fragment might look like a forest, might have trees and birds, but it's functionally degraded, supporting fewer species, and it's slowly losing even those. This relaxation process, where ecosystems adjust to new equilibrium states after disturbance, takes time. We've fragmented vast areas of habitat in the last century or two, but the full impact, the full toll of extinctions this fragmentation will cause hasn't finished playing out yet. Many species and remaining habitat fragments are part of that extinction debt I mentioned. They're still there now, but they're in fragments too small or too isolated to sustain them indefinitely. They will disappear over the coming decades and centuries as the relaxation process continues. And here's what makes this particularly insidious. Even if we stopped all further habitat destruction today, the extinction debt from already fragmented habitats would continue to be paid for centuries. We can't unfragment the landscape easily. We can't restore connectivity across continents that we've carved into patches with roads, farms, and cities. The species already confined to isolated fragments will continue their slow decline toward extinction, regardless of whether we protect what remains. Now let me bring up something that makes all of this even worse: feedback loops and cascading effects. Ecosystems aren't just collections of species, they're networks of interactions. Species depend on each other in complex webs of predation, competition, mutualism, parasitism. When you start removing species from these networks, the effects don't stop with those species. They propagate through the network, causing secondary and tertiary extinctions. This is called co-extinction, and it's one of the least understood but potentially most important drivers of biodiversity loss. When a plant species goes extinct, the specialist insects that depend exclusively on that plant go extinct with it. When those insects disappear, the birds and other predators that relied on them lose a food source. The fungi that had symbiotic relationships with the plant's roots disappear. The entire web of interactions that was centered on that plant collapses, taking multiple other species with it. Some estimates suggest that for every primary extinction, a species going extinct due to direct human impact, there might be multiple co-extinctions of dependent species. So if we directly cause the extinction of, say, 10,000 species through habitat destruction and hunting, the actual total extinction count might be 30 or 50,000 species when you include all the co-extinctions. And those co-extinctions can take a long time to manifest, because dependent species don't disappear instantly when their resources vanish. They decline gradually as their populations can no longer sustain themselves. This creates yet another layer of extinction debt and time lag. We've already removed many species from ecosystems through direct human impacts. The full cascade of co-extinctions those removals will cause hasn't finished playing out. Species that seem fine right now might be slowly declining because something they depend on is already gone or reduced below functional levels. We won't realize they're in trouble until they're also below minimum viable populations and committed to extinction themselves. And then there are feedback loops in the climate system that amplify the initial disturbance. Warming causes permafrost to thaw, releasing methane and CO2, causing more warming. Warming reduces ice cover, reducing Earth's reflectivity, causing more warming. Warming disrupts ocean circulation patterns, potentially triggering rapid climate shifts. Warming increases wildfire frequency, releasing more carbon, causing more warming. We've likely already triggered some of these feedbacks. They'll continue playing out for centuries or millennia, causing additional warming beyond what our direct emissions would cause, creating additional climate stress for species already struggling to adapt. And because these feedbacks involve processes with long time constants, ice sheet dynamics, ocean circulation, carbon cycle responses, they can't be quickly stopped even if we eliminate emissions. They have momentum, just like that boulder rolling downhill. Let me give you a specific example to make this concrete. Coral reefs. Coral reefs are some of the most biodiverse ecosystems on the planet, home to perhaps a quarter of all marine species, despite covering less than 1% of the ocean floor. They're also incredibly sensitive to temperature. When water gets too warm, corals expel their symbiotic algae and bleach white. If the heat stress continues, they die. We've already seen massive coral bleaching events in recent decades, and they're increasing in frequency and severity. The Great Barrier Reef has had multiple major bleaching events in just the past few years. Many reefs globally are now in states of chronic stress, with insufficient time between bleaching events to fully recover. Here's the troubling part. The warming that's already occurred has brought tropical ocean temperatures close to coral tolerance limits. The additional warming we're committed to from emissions already in the atmosphere and from the inertia in the climate system will push temperatures beyond those limits in many regions. Even if we stopped all emissions today, even if we somehow extracted CO2 from the atmosphere and cooled things down, it would take decades for ocean temperatures to respond. Corals don't have decades. Many reef systems will likely be degraded or collapse within the next few decades, regardless of our actions, simply because of climate momentum we can't stop. And when coral reefs collapse, thousands of species that depend on them lose their habitat. Fish species that live in reef structures, invertebrates that shelter in coral colonies, algae and other organisms that grow on reefs, the entire ecosystem collapses with the corals. That's a massive co-extinction event triggered by temperature changes we're already committed to, playing out over the next few decades, unstoppable. Now, I can feel the objection rising. But we can do reef restoration. We can breed heat-tolerant corals. We can reduce other stressors like pollution and overfishing to give reefs a better chance. And yes, all of those things are worth doing. They might save some reefs, might preserve some biodiversity, might slow the collapse. but they won't prevent it entirely. The physics is working against us. The temperature increase is baked in. The thermal stress will continue and intensify. At best, we're talking about damage control, not prevention. And here's the broader point. Coral reefs are just one example. The same logic applies to countless other ecosystems and species. Arctic ecosystems dependent on sea ice. Alpine species adapted to cold mountaintops with nowhere higher to go as temperatures rise. Species in seasonal tropical forests whose rainfall patterns are shifting. Amphibians sensitive to both temperature and moisture changes. The list goes on and on. For many of these species and ecosystems, the environmental changes we've already caused or committed to are sufficient to drive them toward extinction or collapse. We're still in the early phases. The full impact will unfold over the coming decades and centuries. And even our best efforts can only mitigate the severity, not prevent the outcome. Let me introduce another factor that makes this extinction particularly unstoppable: the sheer number of human beings and our resource demands. There are 8 billion people on Earth right now, heading toward perhaps 10 billion by mid-century. Every one of those people needs food, water, shelter, energy. Meeting those needs requires vast amounts of land for agriculture, water extraction from rivers and aquifers, mining for materials, energy production from fossil fuels or alternative sources. Even with maximum efficiency, even with the best technology, sustaining 8 to 10 billion people requires transforming enormous amounts of the planet's surface and resources for human use. There's simply no realistic scenario where we can maintain current or growing human populations at decent living standards without continuing to put pressure on natural ecosystems. We can reduce the per capita impact through renewable energy, sustainable agriculture, circular economies, but we can't reduce it to zero, and with billions of people, even a small per capita impact multiplies to an enormous total impact. This is the fundamental dilemma. As long as human population remains high and resource demands remain substantial, we'll continue displacing natural ecosystems and driving species toward extinction. We can slow the rate, we can try to preserve key habitats and species, but we can't eliminate the pressure. And many species are already so close to extinction thresholds that continued pressure, even reduced pressure, will push them over the edge. Some people argue for massive habitat restoration, rewilding, giving half the Earth back to nature, and that's a beautiful vision with real merit for the species that could be saved by it. But let's be realistic. Restoring habitat on that scale would require displacing agriculture and human settlements from vast areas, which means either radically reducing human population, radically reducing per capita resource consumption, or finding ways to sustainably intensify food production on less land. None of those are quick or easy, and all face enormous political, economic, and social obstacles. In the meantime, while we're hopefully working toward more sustainable systems, species continue going extinct. Habitats continue being degraded. The extinction debt continues accumulating. And the time lags mean that even if we achieved sustainability tomorrow, we'd still experience centuries of delayed extinctions from damage already done. Let me bring up something that's even more troubling from a physics perspective: the thermodynamic reality of ecosystem complexity. Ecosystems are highly ordered, low entropy structures that exist far from thermodynamic equilibrium. Maintaining that order requires constant energy input from the sun via photosynthesis and complex self-organizing processes that took millions of years to evolve. When you disrupt these systems, when you remove species and break ecological relationships, you increase the entropy, you degrade the order. And here's the thing about entropy: it's easy to increase and incredibly difficult to decrease. It's easy to break a complex ecosystem. It's extraordinarily difficult to restore one, because restoration requires not just putting species back, but recreating all the complex interactions and processes that make the system function. We've broken ecosystems across the planet, we've simplified them, degraded them, pushed them toward higher entropy states. Even if we stopped all further damage, even if we actively tried to restore them, the restoration would be incomplete and would take centuries or millennia. Many of the species and interactions we've lost are gone permanently. You can't bring back extinct species. You can't recreate evolutionary relationships that took millions of years to develop. This is why the extinction is unstoppable in a fundamental sense. We've increased the entropy of Earth's biological systems, and you can't just dial that back down. The low entropy, highly ordered, biodiverse state that existed before human impact is not accessible anymore. We've moved the system to a different state, and returning to the previous state would require enormous energy input and time, if it's even possible at all. What we might be able to do is move the system toward a new, stable state that has lower entropy than the degraded state we're heading for if we do nothing. We might be able to preserve some substantial fraction of current biodiversity, maintain some ecosystem functionality, keep the planet habitable and relatively biodiverse. But we're not going to return to pre-human conditions. That ship has sailed. The question is just how degraded the final state will be. Now, I want to address something directly, because I know some of you are thinking, this is depressing. This is paralyzing. If it's all unstoppable, why should we do anything? And that's exactly the wrong conclusion to draw. Let me be very clear. Just because we can't prevent the sixth mass extinction doesn't mean our actions don't matter. They matter enormously. They determine the difference between a catastrophic extinction event and an apocalyptic one. Think of it this way. Imagine you're on a sinking ship. The ship is going down, that's determined. The damage is too severe to stop the sinking. But you still have choices that matter enormously. How many people you get into lifeboats, how much emergency equipment you save, how organized or chaotic the evacuation is. The ship is sinking regardless, but your actions determine whether most people survive or most people die. That's where we are with the sixth extinction. The extinction event is happening, is likely unstoppable in the sense that we'll lose a large fraction of current species regardless of our actions. But we can still determine whether we lose 25% of species or 75%, whether the ecosystems that remain are functional or collapsed, whether the planet that emerges from this extinction is one where human civilization can continue to thrive or one where we're struggling for survival ourselves. Every habitat we protect matters. Every species we save matters. Every ton of CO2 we don't emit matters. Not because these actions will prevent the extinction, they won't, but because they'll reduce its severity, slow its progress, save some fraction of what would otherwise be lost. And that matters both for the intrinsic value of those species and ecosystems and for human well-being, because we depend on functioning ecosystems for countless services: pollination, water purification, climate regulation, food production, disease control. But we need to be honest about what we're doing. We're not preventing a mass extinction. We're engaged in a massive triage operation, trying to save what we can while accepting that we'll lose much that we cannot save. We're determining the severity of the catastrophe, not whether it happens, and that requires different thinking, different strategies, different levels of honesty about what's achievable and what's not. So as we continue, I want to explore the specific mechanisms in more detail, the cascading failures, the tipping points, the irreversible changes, and I want to talk about what triage actually looks like, what we can realistically hope to save, and how we should be thinking about conservation and sustainability in an age of unstoppable extinction. Because understanding the problem is the first step, but the second step is figuring out what meaningful action looks like when you can't prevent the outcome, only influence its severity. So we've established that extinction debt is real, that time lags mean we're still experiencing the consequences of past actions, and that various feedback mechanisms will continue driving species loss for centuries regardless of what we do now. But I want to dig deeper into the specific mechanisms that make this extinction fundamentally different from the previous 5, and more importantly, why those differences make it particularly unstoppable even with our technological capabilities and growing environmental awareness. Let me start with something that doesn't get emphasized enough in popular discussions of extinction. The rate matters as much as the magnitude. You see, previous mass extinctions, even catastrophic ones like the Permian Triassic that killed 96% of marine species, typically unfolded over timescales of tens of thousands to millions of years. That might sound fast in geological terms, but it's actually quite slow in biological terms. It gave species time to adapt, to migrate, to evolve. Some lineages went extinct, but others had the opportunity to adjust to changing conditions or move to more suitable habitats. The current extinction is happening orders of magnitude faster. We're talking about massive biodiversity loss within decades to centuries, not millennia. And this speed changes everything, because adaptation and evolution require time. Natural selection works through generations. Mutations arise. Advantageous ones spread through populations. Species gradually shift their characteristics to match new conditions. But this process takes many, many generations. For organisms with long generation times large mammals, long-lived trees, slow reproducing fish, there simply isn't time to evolve in response to the rapid changes we're imposing on the environment. Let me give you a concrete example. Consider a tree species adapted to a particular temperature and rainfall regime. As climate changes, the suitable climate zone for that species shifts geographically. Maybe it moves northward or upward in elevation as temperatures warm. For the species to survive, the trees need to migrate, which happens through seed dispersal. Seeds germinate in new locations, young trees grow, mature, and eventually reproduce, extending the species' range. But here's the problem. This migration process happens at a certain maximum speed, determined by seed dispersal distances and generation times. For many tree species, the rate might be a few hundred meters per year under ideal conditions. But climate zones are shifting at speeds of several kilometers per year in many regions, 10 times faster or more than trees can migrate. The suitable climate for the species is literally moving away faster than the species can follow it. Now, you might think, well, can't we just plant those trees in their new suitable zones? Can't we help them migrate? And yes, we can do some of that. Assisted migration is a real conservation strategy. But consider the scale. There are tens of thousands of tree species globally, each with different climate requirements, different dispersal mechanisms, different ecological relationships, and trees are just one group. Every plant species, every animal species that depends on specific habitats or climate conditions faces the same mismatch between how fast they can adapt or migrate and how fast conditions are changing. We simply cannot manually assist the migration of every species that needs to move. We don't have the knowledge. Many species are poorly studied or completely unknown to science. We don't have the resources. It would require a conservation effort orders of magnitude larger than anything ever attempted. And we don't have the time. Species are already declining before we've even identified the problem, let alone implemented solutions. This rate mismatch alone condemns many species to extinction. They cannot adapt fast enough, cannot migrate fast enough, and we cannot assist them fast enough. The extinction is baked in by the simple mathematics of rates. Environmental change rate exceeds adaptation rate plus migration rate plus our intervention capacity. When that inequality holds, extinction is the inevitable outcome. Now let me talk about something that makes this even more intractable: tipping points and regime shifts in ecosystems. Many ecological systems don't respond linearly to stress. They remain relatively stable under increasing pressure until suddenly they flip to a completely different state. And once they flipped, returning to the original state is often impossible or requires reducing the stress far below the level that caused the flip in the first place. Think of a lake ecosystem. A lake can absorb a certain amount of nutrient pollution from agricultural runoff, sewage, whatever, and remain relatively clear and healthy with diverse fish and plant communities. But if nutrient input exceeds a critical threshold, the lake can flip into a eutrophic state. Massive algae blooms, oxygen depletion, fish kills, loss of biodiversity. And here's the troubling part. Once a lake has flipped to this degraded state, just reducing nutrient input back to previous levels often doesn't restore it. The algae-dominated state is self-reinforcing. Algae shade out other plants. Their decomposition depletes oxygen, and the system is stuck in the degraded state. To restore the lake, you might need to reduce nutrient inputs far below the original tipping point level, actively remove algae biomass, reintroduce lost species, and even then, restoration might fail because the system has fundamentally changed. This hysteresis where the path forward and the path backward are different is characteristic of many complex systems near tipping points. We've pushed many ecosystems past tipping points already. Tropical forests that have been partially cleared can reach a point where remaining fragments are too dry and fire-prone to persist, flipping to savanna or grassland. Coral reefs stressed by temperature and pollution can flip from coral-dominated to algae-dominated states. Fisheries can collapse and fail to recover even when fishing pressure is reduced. Arctic sea ice may have already passed a tipping point where summer ice cover will continue declining even without further warming, because reduced ice means more solar absorption, more warming, more ice loss. Each of these regime shifts typically involves substantial biodiversity loss. Species adapted to the original state cannot survive in the new state. And because of hysteresis, we can't simply reverse our impacts and expect the ecosystems to return to their previous states. We've pushed systems into new basins of attraction, and getting them back out would require Herculean efforts that may not even be possible. This means that some of the biodiversity loss we're seeing is irreversible on any practical timescale. Even if we achieved perfect environmental stewardship tomorrow, even if we reduced all anthropogenic stressors to zero, some ecosystems would remain in degraded states, unable to support the species they once harbored. The species lost in those regime shifts are gone permanently from those ecosystems, and many may be globally extinct if those ecosystems were their only habitats. Let me bring up another mechanism that I find particularly troubling: the fragmentation of the biosphere into isolated remnants. Before human expansion, most ecosystems existed as relatively continuous expanses: vast forests, extensive grasslands, connected river systems. This continuity allowed species to have large ranges, maintain genetic diversity through gene flow across populations, and shift their distributions in response to environmental changes. We've shattered that continuity. The planet now looks like a jigsaw puzzle, where most pieces have been replaced with human-dominated landscapes, farms, cities, roads, and only small, isolated pieces of natural habitat remain. These fragments are like islands in an ocean of hostile territory that most species cannot cross. Island biogeography theory, developed by E.O. Wilson and Robert MacArthur in the 1960 seconds tells us that species richness on islands reaches an equilibrium between immigration of new species and extinction of existing ones. Smaller islands support fewer species. More isolated islands support fewer species. When you fragment continental ecosystems into island-like patches, they begin following island biogeography rules, and most of our habitat fragments are smaller and more isolated than they would need to be to maintain their current species diversity. This means that fragmented habitats are committed to losing species even if we perfectly protect what remains. The fragments are simply too small and too isolated to maintain viable populations of many species, especially large-bodied species with large territory requirements, low reproductive rates, or specialized habitat needs. Over time, decades to centuries, these species will wink out from the fragments in a relaxation process that's essentially irreversible unless we can somehow restore connectivity or dramatically expand fragment sizes. And here's what makes this particularly insidious. We often don't realize a fragment is too small to sustain a species until the species has already declined below recovery thresholds. A forest fragment might look healthy, might still contain populations of large mammals or specialist birds, but if the fragment is below the critical size needed for those populations to be self-sustaining, they're already doomed. They might persist for decades, the lifetime of current individuals, but without successful reproduction, without recruitment of new individuals to replace those that die, the population slowly ages and then disappears. We call these living dead populations, and they're eerily common in fragmented landscapes around the world. They give a false impression of conservation success. Look, the protected area still has tigers, or the reserve still supports elephants. But the populations are non-viable, slowly declining toward extinction, and there's nothing we can do to save them unless we can dramatically expand and reconnect their habitats. Which, given that the surrounding landscape is now farms, roads, and cities, is often impossible or would require displacing human populations, which creates its own enormous ethical and practical problems. Now let me introduce you to a concept that's absolutely crucial for understanding why this extinction is unstoppable: functional extinction. This is when a species still exists. You can find individual organisms, maybe even sustainable populations in zoos or tiny reserves, but it's ecologically extinct, meaning it no longer plays its role in ecosystems and no longer evolves in response to natural selection. Many large mammal species are functionally extinct already. They exist in such reduced numbers, in such small and managed populations, that they're no longer functioning as evolutionary entities or ecosystem engineers. Elephants in tiny reserves don't shape vegetation and maintain grasslands the way continental populations once did. Tigers in isolated parks don't regulate prey populations across landscapes. Rhinos in protected areas, guarded by armed security, aren't responding to natural selection pressures. They're responding to human management decisions. From an ecological and evolutionary perspective, these species are already gone. They might persist as zoo populations or in highly managed reserves indefinitely, but they're no longer wild animals in any meaningful sense. They're living museums, biological artifacts preserved by human effort rather than self-sustaining components of functioning ecosystems. And here's what troubles me. This might be the fate of most large mammal species, many bird species, numerous reptiles and amphibians, and countless other organisms. As habitats shrink and fragment, as human populations grow and expand, the only way many species will survive is in managed reserves, zoos, gene banks. They'll exist, but they won't be ecologically functional. They won't be wild. They'll be living relics of ecosystems that no longer exist, preserved by human charity rather than ecological viability. Is that really conservation success? Or is it just a slower, more palatable form of extinction? I'm not sure there's a clear answer, but it's a question we need to grapple with because that's where we're heading for many species. The choice isn't between wild populations and extinction. The choice is between managed populations and extinction, between living museums and complete disappearance. Let me talk now about something that amplifies all of these problems: the interaction between multiple stressors. Species aren't just dealing with habitat loss or just climate change or just pollution. They're dealing with all of these simultaneously, and the effects are often synergistic rather than simply additive. For example, Consider a forest fragment that's been isolated by agricultural development. The species in that fragment are already stressed by reduced habitat area, edge effects, isolation from other populations. Now add climate change, which is shifting temperature and rainfall patterns. Species that might have been able to migrate to more suitable climates can't because they're isolated, the surrounding agricultural land is a barrier, so they're stuck in a fragment where conditions are becoming less suitable and they can't leave. Now add invasive species that arrive in the fragment, perhaps in contaminated soil or as hitchhikers on vehicles. These invasives might thrive in the disturbed, warming conditions. They compete with native species already stressed by the other factors, tipping the balance toward extirpation. Now add pollution, atmospheric nitrogen deposition from agriculture and industry, pesticides drifting in from surrounding farms, light and noise pollution from nearby human settlements. Each pollutant has its own effects, but together with the other stressors, they push species beyond tolerance limits. Any one of these stressors might be survivable, but together they create a gauntlet that many species simply cannot run. The interactions are complex and often unpredictable. Two stressors together might have effects that are greater than the sum of their individual effects because one stressor makes species more vulnerable to another, or because together they disrupt critical thresholds or feedback loops. And here's the challenge for conservation. We can't address all these stressors simultaneously for all species in all places. We don't have the resources, the knowledge, or the coordination. So we make choices, protect this habitat, try to slow climate change, regulate some pollutants, but the other stressors continue operating, and the cumulative burden may still push species toward extinction even as we address individual threats. This is why isolated conservation efforts, while valuable, are insufficient. You can protect a reserve perfectly, eliminate all direct threats within its boundaries, and still watch species decline and disappear because of forces operating outside the reserve: climate change, air pollution, loss of migratory connectivity, disruption of regional ecosystem processes. True conservation would require managing entire regions, entire continents, essentially the whole planet, in coordinated ways that maintain all the conditions species need, and we're nowhere close to being able to do that. Let me bring up something that's particularly difficult to discuss, but absolutely essential: the economic and political realities that make stopping this extinction impossible. Conservation competes with other priorities: economic development, poverty alleviation, food security, energy access. In a world with billions of people, many of whom are poor and struggling to meet basic needs, telling them to sacrifice their welfare for the sake of species they've never heard of is a very difficult sell. This creates impossible choices. Do you preserve a forest that's home to endangered species, or do you allow poor farmers to clear it for agriculture so they can feed their families? Do you restrict fishing to protect marine biodiversity, or do you allow fishing communities to maintain their livelihoods? Do you prevent development in biodiverse regions, or do you allow economic growth that might lift people out of poverty? These aren't hypothetical dilemmas. They're daily realities faced by governments, conservation organizations, and local communities around the world. And in almost every case, immediate human needs win out over biodiversity protection because that's the political and economic reality. People care more about their own welfare and that of their communities than about abstract species or ecosystems, especially when they're already struggling economically. This means that conservation efforts are always working against powerful economic and political currents. Every protected area faces pressures for resource extraction, development, agricultural expansion. Every restriction on environmentally damaging activities faces opposition from affected industries and communities. Conservation funding is always limited, always competing with other priorities, always vulnerable to budget cuts when economies struggle or priorities shift. Even in wealthy countries with strong environmental movements, conservation gets a small fraction of government budgets and is often the first thing cut during economic downturns. In poorer countries, where biodiversity is often highest but economic pressures are most intense, conservation is even more precarious. International funding helps, but it's insufficient to address the scale of the challenge, and it often comes with conditions that local governments and communities resent. The brutal truth is this: maintaining high biodiversity requires leaving large areas of the planet in relatively natural states, which means not using them intensively for agriculture, extraction, or development. But with 8 billion people and counting, with billions still living in poverty and aspiring to higher living standards, the pressure to use every available bit of the planet's productive capacity is enormous. Biodiversity conservation is essentially asking humanity to voluntarily constrain our use of the planet, to leave resources unharvested and land undeveloped for the benefit of other species. And we're not doing it. We're not doing it because the incentives don't align, because the benefits are diffuse and long-term while the costs are concentrated and immediate, because international coordination is difficult, because poverty and inequality create desperate situations where environmental protection becomes a luxury people feel they cannot afford. This is why I say the extinction is unstoppable, not just because of ecological mechanisms and time lags, but because the human systems that drive habitat destruction, climate change, and pollution are themselves extremely difficult to change. We know what we need to do: transition to sustainable energy and agriculture, stabilize and eventually reduce population, restore habitats, eliminate pollution, coordinate globally on conservation. But actually doing these things requires overcoming enormous economic, political, and social inertia. Let me be specific about climate change, since it's such a major driver of extinction and it illustrates the problem perfectly. We've known about anthropogenic climate change for decades. The basic physics has been understood since the 19th century. The evidence has been mounting since at least the 1,970 seconds. The scientific consensus has been clear for 30 years or more. And yet, global CO2 emissions are still increasing. We're still building fossil fuel infrastructure. We're still expanding our carbon footprint. Why? Not because we don't know better, but because fossil fuels are deeply embedded in our economies. Because transitioning away from them requires massive investment and disruption. Because the benefits of emissions reduction are global and long-term, while the costs are local and immediate. Because international coordination is difficult when countries have different interests and development levels. Because powerful industries benefit from the status quo and resist change. Because people like cheap energy and convenient transportation more than they care about abstract future climate impacts. We're slowly making progress. Renewable energy is growing. Electric vehicles are becoming more common. Some countries are reducing emissions. But it's too slow. Far too slow to avoid dangerous climate change. Too slow to prevent massive species loss from climate-driven habitat shifts and extreme weather. We're not on track to limit warming to 1.5 degrees Celsius or even 2 degrees Celsius above pre-industrial levels. We're heading for 2.5 degrees Celsius or 3 degrees Celsius or more, which means widespread ecosystem disruption, massive species loss, transformation of the planet's climate zones. And this is with climate change being perhaps the most salient environmental issue, the one that gets the most attention, the most funding, the most policy action. If we can't adequately address climate change despite decades of awareness and effort, what hope is there for addressing the multitude of other drivers of extinction, habitat destruction, pollution, invasive species, overexploitation, many of which get far less attention and resources? The depressing conclusion is that we're not going to adequately address these problems in time to prevent a mass extinction. We'll make partial progress, will slow some trends, will save some species and ecosystems, but the fundamental drivers, human population and consumption, economic systems that externalize environmental costs, political systems that prioritize short-term gains, these will continue pushing us toward further environmental degradation and biodiversity loss. Now, let me introduce something that makes all this even more troubling: nonlinear dynamics and the possibility of cascading collapse. Complex systems like the Earth's biosphere don't necessarily decline gradually and predictably. They can appear stable for a long time under increasing stress, then suddenly collapse when critical thresholds are exceeded, and when one system collapses, it can trigger cascading failures in connected systems. We're seeing hints of this already. The Amazon rainforest appears to be approaching a tipping point where continued deforestation and warming could trigger a transition from rainforest to savanna. This would be catastrophic. The Amazon is home to perhaps 10% of Earth's species, plays a crucial role in global climate regulation, and provides ecosystem services worth trillions of dollars. If it flips to savanna, we lose much of that biodiversity and those services, and we lose them suddenly over decades rather than centuries. Similarly, Arctic ecosystems are rapidly changing as sea ice disappears and permafrost thaws. This isn't just bad for Arctic species, it triggers feedback loops that accelerate climate change globally, affecting ecosystems everywhere. Antarctic ice sheets may be approaching collapse thresholds that would commit us to meters of sea level rise, flooding coastal ecosystems and human settlements alike. Coral reefs globally may be in the early stages of a mass die-off that could see most reefs degraded or dead within a few decades, taking thousands of species with them. Ocean circulation patterns may be slowing, potentially triggering rapid climate shifts. Insect populations are declining precipitously in many regions, threatening pollination and food web stability. Any one of these collapses would be bad enough, but they're interconnected. Amazon collapse accelerates climate change, which accelerates Arctic and Antarctic changes, which further accelerates climate change, which pushes more coral reefs past tolerance limits, which affects tropical marine ecosystems, which affects fish populations, which affects seabirds, which affects island ecosystems. The cascades propagate through the biosphere in ways we can't fully predict. This is what keeps me awake at night. The possibility that we're not just heading for a severe extinction event, but for a systemic collapse where multiple ecosystems fail simultaneously or in rapid succession, triggering runaway biodiversity loss that we cannot stop, even if we suddenly gain the will and resources to try. And here's the terrifying part. Once such a cascade begins, it may be unstoppable regardless of human actions. If the Amazon flips to savanna, we can't simply replant it and expect it to return to rainforest. The local climate will have changed, the soils will have degraded, the species will have been lost. If coral reefs die globally, we can't resurrect them, the species extinctions are permanent, the ecosystem functionality is gone. If permafrost melts and releases gigatons of greenhouse gases, we can't refreeze it and recapture those gases. These are one-way transitions. Once crossed, the thresholds don't allow return. The system settles into a new degraded state and stays there. And because ecosystems are interconnected, one collapse makes others more likely, creating the potential for cascading failures that rapidly transform the biosphere into a much less diverse, much less stable state. This is the nightmare scenario. Not a gradual extinction playing out over centuries that we might partially mitigate through conservation efforts, but a rapid, cascading collapse that fundamentally alters the planet within decades or a few generations, driven by feedbacks and tipping points we've already triggered and can no longer control. I don't know how likely this scenario is. The science is uncertain. We don't fully understand all the relevant thresholds and feedbacks. We can't predict exactly how the system will respond. Maybe the biosphere is more resilient than I fear. Maybe negative feedbacks will stabilize things before catastrophic collapse occurs. Maybe we'll get lucky, but the possibility is real. We're running an uncontrolled experiment on the only biosphere we have, pushing it into states it hasn't occupied for millions of years, triggering changes faster than geological processes normally operate. And once you're running an uncontrolled experiment with complex, nonlinear systems, surprises are not just possible, but likely. And in a system as complex as the Earth's biosphere, surprises tend to be bad. So where does this leave us? We've talked about extinction debt, time lags, rate mismatches, tipping points, fragmentation, multiple stressors, economic and political constraints, and the possibility of cascading collapse. All of these factors point to the same conclusion. The sixth mass extinction is already underway, is driven by mechanisms that will continue operating for decades to centuries regardless of our actions, and cannot be stopped in any meaningful sense. Does this mean we should give up that conservation is pointless? Absolutely not. In the final part, I want to talk about what meaningful action looks like when you can't prevent the outcome, only influence its severity. Because that distinction between prevention and mitigation is crucial, and getting it right might mean the difference between a planet that remains habitable and diverse and one that descends into ecological catastrophe that threatens human civilization itself. So we've established that the sixth mass extinction is fundamentally unstoppable, that the mechanisms driving it are already in motion, that time lags and feedback loops will continue producing extinctions for centuries, regardless of what we do now, and that the human system's underlying environmental destruction are themselves incredibly resistant to the rapid, comprehensive changes that would be required to prevent catastrophic biodiversity loss. Now comes the hardest question: what do we actually do with this knowledge? Because here's what I've learned from physics and from studying complex systems. Knowing that you cannot prevent an outcome doesn't mean your actions don't matter. It means you need to shift from prevention thinking to mitigation thinking, from trying to stop the inevitable to trying to shape how it unfolds. And that shift, intellectually and emotionally, is extraordinarily difficult for most people, including many in the conservation community who've dedicated their lives to protecting nature. Let me start with an analogy from medicine, because I think it illustrates the distinction clearly. Imagine a patient with advanced metastatic cancer. The cancer cannot be cured, it's too widespread, too aggressive, the patient's body too compromised. A doctor who continues to focus exclusively on curing the cancer is missing the point. The meaningful work at that stage is palliative care, managing pain, maintaining quality of life for whatever time remains, helping the patient and family prepare for what's coming. That's not giving up. That's recognizing reality and focusing effort where it can actually make a difference. We're in a similar position with the biosphere. We cannot cure it, we cannot return it to pre-human conditions, cannot prevent massive biodiversity loss, cannot restore what's already been lost or committed to loss, but we can engage in what amounts to planetary palliative care, reducing suffering where possible, preserving what we can, maintaining functionality in critical systems, buying time for adaptation, preparing for the world that's coming rather than the world we've lost. This requires a fundamental reframing of conservation priorities and strategies. Instead of asking, how do we save every species, we need to ask, which species and ecosystems are most critical to save, and how do we maximize our limited conservation resources